What happens if both engines on a jet airliner stop working mid-flight? For many, this question brings to mind dramatic scenes from movies, filled with panic and a sense of impending doom. However, the reality is far less chaotic and grounded in physics and rigorous training. A commercial airliner does not drop from the sky. It becomes a very capable glider. To understand how a plane can fly without engines, we must first understand the four fundamental forces that act on it: lift, weight, thrust, and drag. Lift is the upward force from the wings. It counteracts weight and holds the plane in the sky. Weight is the downward pull of gravity. The other two act on the horizontal axis: thrust and drag. Thrust is the forward push from the engines. Drag is the backward resistance from the air. In normal level flight, these forces balance. Lift equals weight. Thrust equals drag. When both engines fail, thrust disappears. The other three forces remain. Without thrust, drag slows the plane. As speed drops, lift decreases, so the pilot gently lowers the nose. Pointing the nose down creates a forward component of weight, replacing lost thrust for a controlled descent. The plane is now gliding, trading altitude for airspeed to keep generating lift. Still under control, the aircraft descends on a long, gentle, predictable path. Pilots train extensively for this scenario, and the aircraft is designed with multiple safety layers. The flight path changes, but the flight continues under the steady hand of the crew. Once an airliner enters a glide, its performance is measured by the glide ratio. It tells us how far the aircraft can travel forward for every unit of altitude it loses. A typical modern airliner might have a glide ratio around 17:1. That means 1,000 feet down yields about 17,000 feet forward in still air. At 37,000 feet, about 7 miles high, 17:1 can mean roughly 119 miles. This gives a large radius to search for a suitable airport. Pilots maintain best glide speed to maximize distance. Too fast or too slow steepens the descent. Wind matters. A headwind reduces ground range. A tailwind extends it. Pilots and controllers use weather and performance to choose the best, reachable options. This capability is inherent in the jetliner's efficient aerodynamic design: high lift, low drag. The same sleek shape that saves fuel under power makes the aircraft an effective glider when engines are silent. Gliding flight isn't just theory, it's been tested in real emergencies. The most famous example, US Airways, Flight 1549, takeoff from LaGuardia. Minutes later, a flock of Canada geese, near total loss of thrust in both engines, at only about 2,818 feet. Low, slow, dense urban terrain. The crew stayed composed. Captain Chesley, Sully, Sullenberger. First Officer Jeffrey Skiles. Sully took control. My aircraft. Skiles ran the dual engine failure checklist. Priority 1, fly the airplane. Establish best glide. Options assessed with ATC. Sully judged no runway was reachable. We're unable. We're gonna be in the Hudson. A long, flat, open path. From strike to touchdown. About 3.5 minutes. Energy perfectly managed. Lined up over the George Washington Bridge. The ditching left the aircraft intact. All 155 aboard were rescued. The miracle on the Hudson proved control and training can prevail. When a dual-engine failure occurs, pilots rely on training and clear procedures. Quick reference handbook, checklists for non-normal situations. Fly the airplane, maintain correct pitch, maintain correct airspeed, establish a stable glide. One pilot flies while the other begins diagnostics and recovery. Announce the failure, start the checklist, and attempt an engine restart. Check fuel switches, activate backup pumps, try windmilling to relight, start the APU to provide electrical power and bleed air to aid restart. Declare Mayday. ATC clears traffic and provides nearest airports, distance, bearing, runway conditions. Pilots continuously calculate if altitude is sufficient to reach a runway. If not, prepare for an off-airport landing or a powerless landing at an airport. Configure for landing. Extend flaps and slats to slow for a gentle touchdown. Use backup power as needed. Flight attendants secure the cabin and brief the brace position. Every step is deliberate and coordinated. The calm resolution of dual-engine failures reflects aircraft redundancy, backups for critical systems. Beyond the main engines, the APU can power instruments, navigation, and radios. The RAT provides emergency electrical and hydraulic power. Even in a power-out scenario, pilots retain flight displays and the hydraulic muscle to control the aircraft. Engines undergo extreme certification tests and strict maintenance based on hours and cycles, with data monitored for early signs. Airline pilots train recurrently, practicing dual-engine failures, checklists, glides, and powerless landings until second nature. These layers, design, certification, maintenance, and pilot training, make simultaneous, unprovoked dual-engine failure extraordinarily unlikely. Losing both engines does not mean falling from the sky. The jet transitions into a large, efficient glider. Aerodynamics still work. By lowering the nose, gravity maintains the speed needed to fly. From high altitude, the aircraft can glide vast distances, giving crews options and time. Pilots follow precise procedures. Redundant systems support control and navigation. Planes do not fall, they glide. Subscribe for more aviation theory explained clearly.